All right, welcome back to the review session, everybody. Here's problem two. We'll just go right into it. So we have air bubbles discharging from the end of a submerged tube as shown below. The bubble diameter d is assumed to be a function of the airflow rate. So is a function of the airflow rate q, tube diameter d, the acceleration of gravity g, the density of the fluid rho, and the surface tension of the liquid sigma. Determine a suitable set of dimensionless variables for this problem. That's part A. And then B is model tests are to be run on Earth for a prototype that is to be operated on a planet where the acceleration of gravity is 10 times greater than that on Earth, right? And the model and prototype are to use the same fluid, and the prototype tube diameter is to be 0.25 inches. Determine the tube diameter for the model and the required model flow rate if the prototype flow rate is to be 0.001 feet cubed per second. All right. So anytime we'll start with part A, set up our dimensionless variables, and then we'll do part B. So anytime that we have dimensionless variables, we need to define all of our variables by their dimensions. And here we're gonna use F, L, and T, right? Because we have our dimensions are given in English units, right? Feet and feet. If they give anything to you in meters, then you're going to use mass, length, and time. But here we're using non-SI units. All right. So diameter is a length. Flow rate is length cubed per time. Little diameter is also a length. Gravity is an acceleration, so that's length per time squared. Rho, density is force times squared per length to the fourth. It's either something you can memorize or just work backwards from knowing that that density is mass over volume. So, yep. And sigma is surface tension, which is force per length. I'm not sure if we've seen that one yet, but that might be a good one to remember. If you're ever confused on what the dimensions of a variable are, though, I don't know how Dr. Schaefer is doing questions mid-exam, but yeah, that'd be something worth asking. I don't think he's not testing you on remembering dimensions. He's just testing you on if you can get to density, because we know the dimensions of density, right? But maybe not surface tension. Anyway, that's not the point of the problem. So now what we do is, we have 6 variables, and then there are 3 reference dimensions that we're using. So we need 3 pi terms in this problem. And then we got to pick repeating variables, which represent each of our reference dimensions. So in this case, I chose, let me write that down. So reference dimensions, reference variables. I chose gravity for our time. Then we chose this diameter for our length. And then to represent force, we use sigma. Those just seem to be the easiest. And most of the time when you're setting up reference dimensions, you want to use the stuff that's here on the right. So even though we could have used cap D instead of low D for our reference variable, I don't know. This is just the practice that we're going with. If you want to do it the other way, you can do that, but it doesn't really make a difference to me. So, by inspection, we notice that let's see if that can focus. One of our pi terms is just going to be a length over a length. That's a dimensionless variable. That includes a reference variable and a non-reference variable. Or repeating variable? Yeah, that should be a repeating variable. Doesn't make a huge difference, but we'll do it right. All right, so that's our first pi term. We have 2 to go. So our second pi term, we'll find that for q. Then we say g to the a, d to the b, sigma to the c, and that's going to be pi 2. And then plugging in each of the dimensions for these, from our handy reference table. Notice how I put a dot over the equal sign. I'm not guaranteeing Dr. Schaefer will take off points if you don't use the dot when you're referencing these dimensions as equal to something, but it's good practice either way. And that'd be something he'd take off points for, knowing him. All right. So then we just walk through and looking at length. So we have one length from A, one length from B, and a negative, right? Because it's the denominator for C. Let's see, for time, -1 minus 2a, that's 0. And then for force, we have c equals 0. So we get a is equal to -1/2, b is equal to -5/2. My allergies are starting to kill me. Anyway, so we get, plugging in each of our dimensions for, each of our exponents for our dimensions, we get q over square root of g times d to the 5/2. Alrighty. What do we have next? All right, pi 3. So we've used d, q, and the one we're left with is rho. So rho, g to the a, d to the b, sigma to the c is pi 3. Well, I wrote that over there. So pi 3 is defined as ft squared over L to the fourth, g L per t squared to the a, L to the b, FL to c. And same process as before. We're going to set up our variables, or sorry, not our variables, our system of equations. Solve that a is 1, c is -1, and b is 2. Kind of through that because I already did them in my notes, but go back and check me on that. So pi over 3 rho g d squared over q. So for our part A, our answer is going to be d over d is a function of our other 2 pi terms, which is rho g d squared over q, and q over, wait a second, we didn't even have q in this one. Let me see here. Let me figure this out. One sec. I might have made a mistake in my notes. All right, we'll just re-record this.